So earlier in the last few videos, or in the earlier videos, or in the earlier topics, we talked about if we had a curved beam that we applied a 250 newton meter load to, um, and the uh, we had we could calculate, and we knew the geometry, we knew the inner radius, and we knew the cross sectional area. We could calculate um, the eccentricity, the radius to the centroid, the radius to the neutral axis, and the cross sectional area. So we can determine sigma theta uh, for along AA using the following equation. So we defined this in the last topic where we had, or the last video that we defined uh, the tangential stress as being equal to uh, negative m over a e times Rn minus R over R. Now, if we distribute or divide both Rn and R by R, we end up getting this equation here, where we get m Rn divided by AER plus m over AE. Now, notice here that um, that um, the only term that changes in this whole equation here is R. So R is the only non-constant, or the only variable. Everything else is a constant, okay? So the only thing that will change. Okay, so when you're calculating these equations, you can just you can calculate, I guess, basically these two coefficients, or these two terms here, and then you can just change R to calculate sigma theta. Okay, so for when R is equal to 150 millimeters, here sigma theta is going to be equal to negative 250 newton meters times 173.803 times 10 to the negative third meters divided by 5 times 10 to the minus fourth meters. So that's our area times our eccentricity, which I'm going to write as 1.20 times 10 to the negative 3 meters. All right, and then our radius that we're plugging it in here, so this is our variable, would be equal to 150 0.150 meters. Okay, and then we had to add in our additional term here. All right, which is just going to be equal to negative 250 newton meters divided by 5 times 10 to the minus 4 meters times 1.20 times 10 to the minus 3 meters. All right, so if you evaluate all that, so this should be meters squared here. All right, so if we evaluate all these out, what we'll end up getting is we'll get sigma theta is going to be equal to 66.3 megapascals. Okay. All right, and then we can repeat this process for R is equal to 200 millimeters. So if we do that, we get sigma theta would be equal to, most of these terms are going to be the same, so we still have our 250 nanometer moment. We still have 173 times uh, 0.803 times 10 to the minus third meters. And then on the bottom, we're going to get 5 times 10 to the minus 4 meters squared times 1.20 times 10 to the minus 3 meters. And then our radius this time is going to be equal to 0.200 meters. So that's our variable, R. right? And then the rest of the equation is just going to be the same. It'll be the minus 250 newton meters over 5 times 10 to the minus 4th meters squared times our eccentricity of 1.20 times 10 to the minus 3rd meters. All right, so if you evaluate all out, we get minus 54.7 megapascals. All right. All right. So notice that unlike the case of like a symmetric cross section and bending for a straight beam, you notice that the magnitudes of these two stresses due to bending are the magnitudes of both of these stresses are not equal to each other. All right. So um, so so you depending on the direction of your bending moment and the direction or the location of your centroidal axis, your bending stresses will not be equal in magnitude on the far end of your cross section or on the inside of your cross section.